Today I will discuss about Poynting vector, wave equation, and the propagation of the wave through the different mediums. What are the different equations we are using to find out the phase velocity, the phase constant, and also the attenuation constant and phase constant. What it means by the attenuation constant? All these points will be discussed here. Okay, now first of all, we will see that the Poynting vector or Poynting theorem. Now, this theorem is used to find out the power present in the specific region. If you know the electric field and the magnetic field, then it is possible to find out the power present in the specific region or inside of the volume. Okay, now, yes. Therefore, first of all, we will see the equation for that one because the derivation is not necessary to you, and just the objective type questions will be asked, and the problem, numerical problem, will be there, so that you should know the equation of the total power, how we can find out the total power present inside the specific region. Okay, now at the end of the derivation of this Poynting equation, that is the equation we will get, that is the closed surface integral E cross H is equal to minus dou by dou t volume integral in bracket 1 by 2 epsilon E square plus 1 by 2 mu into H square bracket close dv minus sigma E square, volume integral of sigma E square. Now the meaning of this equation is that total power is equal to rate of decrease in energy stored in magnetic and electric field minus ohmic losses. Now this is the meaning of this equation. Okay. Now left side of this equation represent the closed surface integral of the Poynting vector, and therefore the Poynting vector is P is equal to E cross H. And right side of these equations are having three terms. That is, the first term is the related to that of the electric energy and magnetic energy, sum of these two energies, because electric energy is given by 1 by 2 epsilon E square, and the magnetic energy is given by that of 1 by 2 mu into H square. Now this energy is decreasing with respect to that of the time, and we have taken the volume integral of this uh, rate of decreasing the magnetic energy and electric energy. And third term is the ohmic losses. Now this term is whenever there is the medium is conducting, at that time some loss will be there. That loss is called as the ohmic loss, and that ohmic loss is determined. A total ohmic loss we can determine by taking the volume integral of sigma into E square. If you know the electric field intensity and the sigma, you can find out the ohmic losses. The ohmic loss is not present in that of the free space because the free space is not a conducting medium. Okay. Now, therefore, this is the one of the equation that is Poynting theorem. Now, we can also describe the Poynting theorem or Poynting vector means what actually? P is equal to E cross H. Now, here E is nothing but the electric field intensity vector, and H is the magnetic field intensity vector, and P is the Poynting vector. Now, the direction of this Poynting vector is perpendicular to both electric field and the magnetic field. In another way, you can say that these three vectors are orthogonal to that of the each others. Now, suppose that electric field is along that of the x-axis, and if a magnetic field is along that of the y-axis, then the Poynting vector should be along that of the z-axis. Okay. Now, your Poynting vector also represent the direction of the wave propagation, and the here we are considering that the plane uniform, that is the electromagnetic wave, is the uniform plane wave, means that the phase and the amplitude is constant over the plane. Uh, Therefore, that type of the electromagnetic wave we are calling as the uniform plane wave. Okay, now the unit of this Poynting vector is watts per meter square. Now, suppose that the Poynting vector is given to you, and if you want to find out the total power present in the cube or total power present inside that the sphere, okay, or total power coming outside that of the closed surface, then you have to take the volume integral of that Poynting vector, so that you will get the total power present, total power or net power outside, net power out of that closed surface. Okay, and therefore this is the one of the equation, that is the Poynting theorem. And you can find out. Now suppose if you want to find out the power present, there is basically there are two types of the powers, the real power and imaginary power. But the real power is propagating, and we are calculating only the real power. Okay, now here also that is the equations for that of the electric field and magnetic fields are given. And if there is the medium is the free space, then that average power we can find out by using this equation. I will show that equation, that by using that equation you can find out the average power. Okay, now here I will show it, that equation for that of the average power. Okay, now this is the equation. Now P average is equal to E naught square divided by 2 into mod of eta. Eta is the intrinsic impedance. Now here whenever the medium is the free space, at that time this quantity will become 1. Okay, and therefore to find out the average power in that of the free space, we can use this equation, E naught square divided by 2 into eta. Okay, now this Z alpha is also 0, theta is also 0, that is the phase angle between that of the electric field and magnetic field is also 0 in that of the free space, and therefore this term will becomes 1. And Az represent the direction of that wave propagation. Okay, you can use this equation to find out the average power or the real power present in the free space. Now we will see that the wave equation. Okay, now we'll see the wave equation means what is that wave equation. And that wave equation, Helmholtz wave equation, first of all we will see that. Then afterwards we will see the uh, differential form, the wave equation, and then the solution of this differential equation is nothing but your the equation of that wave which is propagating through that of the free space. Okay, now therefore first of all we will see that the wave equation, or now this wave equation is nothing but the equation of that electromagnetic wave which is propagating through that of the free space. Now first of all we have obtained the wave equation for that of the lossy dielectric medium and isotropic medium, imperfect medium. Okay, and for which some Maxwell's equations are satisfied by this medium. Okay, and then we have obtained the Helmholtz wave equation. Okay, now first we will see that actually the Helmholtz wave equation. Okay, because the derivation will not be there, and in your exams, okay, objective type questions will be there. We have to identify, suppose that there is the you can identify the wave equation. Now this is the wave equations which we have obtained, that is del square Es minus that is lambda square, lambda gamma square Es is equal to 0. Now here del is nothing but the differential operator, that is dou by dou in a rectangular coordinate system. Del is equal to dou by dou x, uh, dou by dou y, dou by dou z. Okay, of Es we have to take, and that is del operator, and this is the uh, your gamma. Okay, and this gamma is called as the propagation constant of that wave. Now this equation which we have written here, this equation is in the this is the equation of that wave inter vector form. Now this equation is in that of the vector form. Okay, now here gamma is nothing but your propagation constant. Okay, and is called as the propagation constant of the medium, and propagation constant of the medium we can this is the equation for that one. Gamma square is equal to j omega mu in bracket sigma plus j omega epsilon. Okay, sigma is nothing but the conductivity of the medium, and epsilon is the permittivity, omega is the frequency of the angular frequency of the wave which is propagating through that medium. Okay, now this is the totally imaginary quantity. You can say that this is the j. If there is j means that the quantity is imaginary. Okay, now similarly also we can obtain the wave equation del square hs minus gamma square hs. Now here es and hs is the phasor quantity. Phasor quantity means it is having the magnitude and also the phase for that electric fields and the magnetic fields. Okay, now therefore this is another wave equation which is in the vector form. Del square hs square minus gamma square hs is equal to 0. Now these are the two equations are called as the Helmholtz wave equations. Okay, now equation number 9 and 10 is known as the homogeneous vector Helmholtz equation, or simply vector wave equation. Now this is the vector wave equation. We have seen that where that two equations we have seen that in which there is the propagation constant gamma. Okay, now this propagation constant, we will see that separately. That is what is the equation for that of the propagation constant. Now and is having the real part and imaginary part. If you separate out the real and imaginary part of that propagation constant gamma, then the equation for that gamma will be alpha plus j beta. Now this for this particular equation is having separate derivation, that is to extract the real part and imaginary part, but we have to only remember this equation for that of the propagation constant. Okay, that is propagation constant is having the real part is alpha, and this alpha is known as the attenuation constant of the medium. Means how this it will measure the how the wave is attenuating per unit distance. That quantity is determined by using this attenuation constant, and then there is also the phase constant. Now this phase constant means per unit distance how much phase will be changed of that wave is denoted by this beta. Now therefore this propagation constant is combination of the two constants, that is attenuation constant and that of the phase constant, and therefore we are saying that this is the propagation constant gamma. Okay, now therefore here we have seen the equations for that of the wave equation. Okay, in the vector form. Now we can also obtain the equation. Now you can see that first of all we will see the equation for that of the attenuation constant. Okay, now the equation for that of the attenuation constant alpha is equal to omega into under root of mu epsilon divided by 2 in bracket square root of 1 plus sigma divided by omega epsilon raised square, and out of this square root minus is there, and then bracket close. Okay, alpha, and then beta is equal to omega square root of mu epsilon divided by 2 in bracket square root of 1 plus sigma by omega epsilon whole square plus 1. Now if you observe this equation, there is only one difference between these two equations, that is in the first equation minus sign is used minus 1, and in the second equation only plus sign. Okay, therefore to remember these equations for that of the alpha and beta, you can easily uh, remember these equations to find out the alpha and beta for any uh, wave which is propagating through any particular medium. Okay, and for this to find out the alpha and beta, we should know the characteristic or the properties of that medium, that is nothing but your mu and epsilon. then also sigma conductivity, and also you should know the what is the frequency of that wave which is propagating through that of the medium. All these quantities or the parameters should be known to you. Then you can find out the attenuation constant and also the phase constant. Okay, now these are the equations. You can also note down these two equations. It's called as the attenuation constant and phase constant of the wave which is propagating through that of the medium. Now we'll see that the wave equation in the differential form. Now actually that they'll represent. Now suppose that we are considering the wave is propagating uh, uh, towards that of the z axis, okay, and the electric field component is along that of the x axis. Then the equation for that of the electric field intensity in the phasor form, Es is equal to Exs of Z into Ax. Ax represent the direction of that electric field intensity, and this that electric field intensity is only the function of this Z, uh, and therefore we have written here the equation in the phasor form is having the component only along that of the x-axis. Okay, now now we will see that the equation in differential form. What is the equation for that of the wave in that of the differential form? Okay. Now we have to remember the equation in vector form. First of all, that is it is called as the vector wave equation. That is the del square of Exs minus del square of minus y square gamma square Ex. Yes. Okay. This just we have taken common Exs of z. Then what you will get del square minus y square in bracket. Now actually the wave is propagating towards that of the z axis. Okay, and therefore and electric field intensity. Okay, therefore electric field intensity is uh, constant over that of the plane along that of the x axis. Okay, and therefore if you take the differentiation, that is double differentiation of Exs of z with respect to that of the x, then this differentiation will become zero because there is no change. Okay, no change along that of the x and y, and therefore there is change only along that of the z axis, and therefore these two differentiations are zero. Okay, and therefore the equation will becomes that is dou square by dou z square minus gamma square e in bracket close exs of z is equal to 0. Now this equation you will get finally, that is the this is the equation of the wave in the differential form, or this is also called as linear homogeneous differential equation of the wave. Okay, and where exs is nothing but your electric field intensity, which is the function of only z. Okay, and this is the partial linear partial differential equation. Now if you solve this linear partial differential equation, after solving this linear partial differential equation, linear homogeneous differential equation, the solution of this differential equation will be exs of z is equal to e naught e to the power of minus gamma z plus e naught dash e to the power of gamma z. Okay, where e naught and e naught dash are the constants. Okay, now the facts is that the field must be finite at infinite requires that e naught dash is equal to 0. Alternatively, e to the power of gamma z denote the wave is traveling in the negative z direction. Now here actually the second term represent that the wave is traveling in that of the, when we are solving the equations actually this term you will get, but actually what we have considered, the wave is propagating only towards that of the plus z direction, and therefore the second term will be the 0 we have to consider. Okay, and therefore the equation for wave is propagating only towards that of the plus z direction. Okay, now therefore e naught dash is equal to 0, and therefore second term is also 0. And if you add the time factor, now time factor e to the power of j omega t in the equation. Okay, and also we can replace this gamma by that of the alpha plus j beta. Then the equation will becomes, okay, now we can see that here, now e of z of t is equal to real part. Just we are considering the real part, not imaginary part. Okay, and exs of z e to the power of j omega t ax. Okay, now this equation is expanded. Now actually exs of z is nothing but is phasor quantity. Now this is the phasor quantity e naught into e to the power of minus gamma z. Okay, now then afterwards we have expanded this equation. We have considered, just we have substituted here gamma is equal to alpha plus j beta and e to the power of j omega t, and then uh, we have expanded, that is we have converted this exponential quantity into that of the trigonometry quantity. Okay, there is the equation which will convert actually this exponential equation into that of the trigonometry. Now whenever we are there is a question of real part, then you will get only that e naught into e to the power of minus alpha z cos of omega t minus beta z ax. Now this is the standard equation of the wave which is propagating through that of the medium, because this is the real part. Okay, real part is propagating, that is the imaginary part, real power is propagating through that of the medium, and the real part of the electric field intensity equation is e naught into e to the power of minus alpha z cos of omega t minus beta z. Okay, now how this wave is propagating, we can also see here. Now this is your actually x-axis, okay, and this is your z with respect to that of the z. As the z increases, then the magnitude of the electric field intensity is also decreasing. You can see here that is the its magnitude is decreasing with respect to that of the z. Okay, and that x-axis, and only the component is present along that of the x-axis of that electric field intensity. Okay, now E naught represent the maximum amplitude of electric field intensity. Now here omega is the angular frequency of the wave which is propagating through that of the medium. Alpha is the attenuation constant of the medium. Beta is the phase constant of the medium. Okay, and these are the parameters of that waves. Okay, so that if you know all these parameters, then you can also find out its magnitude, okay, at any specific point. Okay, now these are the this is the equation for that of the E. Now what is the equation for that of the H also we have to see. Okay, now there is a relation between that of the electric magnitude of electric field intensity and magnitude of magnetic field intensity, and that relation is given by this equation. Now H naught is equal to E naught divided by eta. Now eta is equal to E naught divided by H naught. Eta is nothing but the intrinsic impedance of the medium. Okay, now therefore we have to consider only the real part, and therefore the equation for that of the magnetic field intensity will becomes. Now we have to remember this equation, that which will give the relation between, that is the electric field magnitude of electric field intensity, and that is maximum amplitude of electric field intensity and maximum amplitude of magnetic field intensity. Okay, and then we can write the equation for the magnetic field intensity, and we have written here. You can see that the equation for that of the magnetic field intensity, which is the real part only, h naught into e to the power of minus alpha z e to the power of j omega t minus beta z. Okay, now the we have considered that wave is propagating through that of the lossy dielectric medium, and whenever the wave is propagating through that of the lossy dielectric medium, that intrinsic impedance quantity is the actually having real part and imaginary part. Okay, and therefore that intrinsic impedance, that is the equation for that of the intrinsic impedance, is under root of j omega mu divided by gamma plus j omega epsilon. Now this equation also we have to remember, okay, because actually this is the equation for intrinsic impedance for lossy dielectric medium. Okay, now theta n is nothing but the phase angle. Okay, whenever there is the quantity in terms of real and imaginary part, there is some phase angle. Okay, now that phase angle is theta n. Now if you calculate the magnitude, okay, magnitude, then what you will get? You will get the equation square root of mu divided by epsilon 1 plus sigma divided by omega epsilon whole square raised to 1 by 4. Now this is the magnitude, okay, magnitude of the intrinsic impedance for that of the lossy dielectric medium. Now we have to remember this equation also. Okay, sometimes actually if you want to find out if there is a question at that time, you can use this equation. Now here theta n is the angle. Now this theta n, tan of 2 theta n is equal to sigma divided by omega into epsilon. Okay, now this angle, or this is the phase angle between that of the electric field and the magnetic field, and the range of this angle is from 0 to 45 degree. Okay, now therefore theta n range is only from 0 to 45. And how we can find out it? It is depends upon that of the conductivity of the medium. It is also depends upon that of the permittivity of the medium and angular frequency of the wave which is propagating through that of the medium. Then we can find out the phase angle between, by using this equation you can find out the phase angle between that of the electric field and the magnetic field. Okay, by using this equation it is possible. If you know these three parameters, then it is possible to find out the phase angle between that of the electric field and the magnetic field. Okay, now therefore for that of the lossy dielectric medium, the equation for magnetic field intensity will be H is equal to E naught divided by mod eta. Mod means magnitude we have considered e to the power of minus alpha z cos of omega t minus beta z. Theta n is nothing but the phase angle between that of the E and H. Now these are the equations for that of the E, standard equation for that of the E and H for lossy homogeneous dielectric medium. Okay, now therefore we have seen the equations for that of the E and H, standard equation for that of the waves which are propagating through that of through lossy dielectric medium. Our same equation is reduced depending upon the type of the medium, that is for E and H. Okay, now these are the wave which is propagating along that of the z axis. Now uh, means that actually e to the power of minus alpha z, e to the power of e to the power of minus alpha z represent actually the amplitude is decreasing or attenuating, or its amplitude is decreasing by the factor e to the power of minus alpha z. Okay, and this is the factor by which actually that amplitude of that wave or electric field or magnetic field is decreasing. Okay, at what factor that amplitude is decreasing, at what rate the amplitude is decreasing, it is depends upon that of the alpha value. Okay, hence alpha is known as the attenuation constant. Okay, now what is the unit of attenuation constant, or it is also called as the attenuation coefficient of the medium. Okay, and it is the measure of spatial rate of decay of wave in the medium measured in Nepers per meter. Now, actually, this is measured, that attenuation constant is measured in Nepers per meter. Another unit for this one is that decibel per meter. Now, there is also an attenuation of 1 Naper denotes that there is the reduction to e to the power of minus 1. Whenever the power of e is minus 1, then we are saying that the 1 Naper power is reduced. 1 Naper that power or the amplitude is reduced. Okay, now therefore we can convert it Naper into that of the decibel by using this equation. 1 Naper is equal to 20 log to the base E. Okay, it will be 8.686 dB. Means 1 Naper is equal to 8.6. We have to remember it. Okay, 1 Naper is equal to 8.686 dB. Okay, now and 1 Nepper denotes the reduction to e to the power of minus 1 of the original value. Okay, original value, by this factor you have to multiply so that you will get the value in decibel, and we have converted into that of the decibel value by taking a log 20 log of e to the base 10, then you will get this 8.686. Now this is the attenuation constant or of the wave which is propagating through that of the medium. Now another parameter of this wave is the phase constant. Okay, now the phase constant is denoted by that of the beta, is the measure of the phase shift per unit length, means how much phase is changing per unit length of that wave which is propagating through that of the medium, is called as the phase constant, or it is also called as the wave number or wave velocity. Okay, now therefore the phase constant beta, the wave velocity is omega divided by beta. Okay, and therefore omega is nothing but 2 pi by f, and beta is 2 pi by lambda, and therefore the wave velocity is equal to lambda into f. Okay, now lambda is equal to 2 pi by beta. Okay, now therefore that is E and H are out of phase by that of the theta n is the phase angle. Okay, we have seen that, and we have seen the intrinsic impedance is nothing but the ratio of the E and H, and also E leads H by an angle theta whenever the wave is propagating through that of the lossy dielectric medium. Now another equation for that of the lossy dielectric medium is that whenever the magnitude of conduction current density to that of the displacement current density is equal to sigma Es divided by j omega epsilon into Es. Now Es will get cancelled, and therefore the ratio of these two current densities, okay, displacement current densities exist because there is the time varying field is there, and because of this time varying field, the there is also displacement current density, and the equation for this ratio is given by Jc divided by Jd is equal to sigma divided by omega into epsilon. Both are the vectors. Jc is also one of the vector. Jd is also one of the vector. Now to identify the conduction losses or dielectric losses are minimum or maximum, we are using one of the term that is called as tangent, loss tangent. Okay, loss tangent of the particular medium, which is nothing but that is tan theta is equal to sigma divided by omega into epsilon. Now theta is nothing but actually the angle made by this current. Okay, actual current or resultant current with respect to that of the displacement current density. Now if you measure the angle between that of these two vectors, now this is the resultant vector, this is the conduction current density, this is your actually displacement current density, and there is some angle made by this resultant current with respect to that of the displacement current density. Depending upon this angle, actually the dielectric losses depends. Okay, now here tan theta is called as the loss tangent. Okay, theta is the called as the loss angle of the medium. Medium is said to be good or lossless or perfect dielectric if tan theta is very small. Okay, tan theta is when tan theta is very small or loss tangent is very small, then we are saying that the medium is good or perfect. Okay, for that of the perfect and is loss tangent is very small. Okay, now sigma is far less than that of the omega into epsilon. For this particular case, when the sigma, that is the conductivity of that medium, that is the when we are saying that the dielectric losses are very less, means that sigma is far less than that of the omega into epsilon. At that time, we are saying that the medium is perfect. Okay, now when the medium is good conducting medium, then sigma, that is the conductivity of the medium, is far far greater than that of the omega into epsilon. Okay, in that case, loss tangent is greater. Okay, that is tan theta value is very large. You will get, therefore, these are the two techniques actually. This is the one of the technique to identify the type of the medium, whether that medium is perfect dielectric medium or the perfect good conducting medium. Okay, you can identify just by using this equation. That is, if the sigma is far far less than that of the omega into epsilon, then we can say that the medium is perfect dielectric medium. And if sigma is far far greater than that of the omega into epsilon, then we can identify that the medium is good conducting medium. Okay, now this is the one of the equation which will be useful to solve the problems. Okay, because sometimes the question may be asked to find out the displacement current density. At that time, you should remember this equation. Okay, now this is the magnitude, the ratio of this magnitude represent tan theta and sigma divided by omega into epsilon. Okay, and from that one we can find out the displacement current density, conduction current density, and also we can determine whether we can also judge that whether this particular medium is good conducting or perfect dielectric. Okay, now we will see that actually the wave propagation through that of the different mediums. Okay, now first of all we will see that the wave propagation through that of the lossless dielectric medium. Okay, lossless dielectric medium. First of all, we have to see the what are the characteristics of the lossless dielectric medium. Okay, lossless dielectric medium means what actually? The sigma is approximately zero. Okay, sigma is approximately zero means that there is no conductivity for that of the lossless medium. Okay, lossless dielectric medium, but there is some permittivity, and permittivity is equal to absolute permittivity epsilon is equal to epsilon naught into epsilon r. Okay, mu is equal to mu naught into mu r. Now we have to see the equation for that of the attenuation constant, phase constant, then also phase velocity. Okay, for that of the when the wave is propagating through that of the lossless medium. When the wave is propagating through that of the lossless medium or perfect dielectric medium, then your attenuation constant alpha will be 0. Beta is equal to omega into under root of mu into epsilon. We have to remember all these equations actually if the numericals are there. Now the phase velocity is equal to 1 upon under root of mu into epsilon. Now the wavelength is 2 pi by beta, or beta is equal to 2 pi by lambda. Okay, and intrinsic impedance is equal to under root of mu divided by epsilon. The medium is lossless and therefore there is no phase angle or the real quantity, and therefore this angle is 0. Okay, now these are the equations we have to remember to find out the alpha, beta, that is the alpha attenuation constant, phase constant of the wave, and the phase velocity 1 upon under root of mu into epsilon, and the wavelength, and also the intrinsic impedance. Okay, to find out the intrinsic impedance, we have to remember this equation. Okay, under root of mu divided by epsilon. Okay, then another case that when the wave is propagating through that of the free space. Okay, what are the characteristic of that one? When the wave is propagating through that of the free space, then what happens actually? The sigma is equal to 0, mu is equal to mu naught, epsilon is equal to epsilon naught, and therefore when the wave is propagating through that of the free space, the alpha is also 0, attenuation constant alpha is also 0. Okay, and beta is equal to omega into under root of mu naught into epsilon naught, and therefore it will becomes actually omega divided by c, because c is nothing but the phase velocity. Okay, therefore you can also write that phase constant is also equal to that of the omega divided by c. Then phase velocity is equal to 1 upon under root of mu naught into epsilon naught. that is nothing but the velocity of the wave, and therefore that value is 3 into 10 to the power of 8 meter per second. That is the velocity of the light which is propagating through that of the free space. Okay, and therefore and after substituting actually mu naught and epsilon naught constants, okay, you will get intrinsic impedance for that of the free space is equal to 120 pi or 377 ohm. Okay, now the equation for that of the electric field intensity when wave is propagating through that of the free space is E naught cos of omega t minus beta z ax, and h is equal to h naught cos of omega t minus beta z, or in another way also you can write that E naught divided by eta naught is equal to 120 pi here. Okay, cos of omega t minus beta z ay is nothing but actually it will show the direction of the magnetic field intensity. Okay, now we can also plot this field. Actually both fields are perpendicular to that of the each other. Okay, and they are propagating in the free space. Okay, now the direction of the propagation vector is along that of the z-axis. Okay, suppose that now in general, if you want to identify the direction of the fields, that is the electric fields, magnetic field, and pointing vector, then also we have to use here this diagram. When we are going to the top the clockwise direction, then you will get the positive cross product. When you are going negative direction, then you will get the cross product negative. Okay, and from that one you can understand the sign of the particular field. Okay, now here these are the wave propagation through that of the free space. Now then wave propagation through that of the good conductor, what are the equation, how the equations for that of the alpha, beta and that of the phase velocity is reduced when we are considering the wave is propagating through that of the good conductor. Okay, now when the wave is propagating through that of the good conductor means that what are the characteristic, first of all we have to understand sigma, that is the conductivity of that particular medium is very high or infinity. Okay, and epsilon, the permittivity is equal to epsilon naught, mu is equal to mu naught into mu r. These are the characteristic of good conducting medium. Your sigma is equal to infinity, and if you substitute in the main equation all these parameters, then the equation for that of the alpha and beta will becomes, it is under root of omega mu into epsilon divided by 2. Okay, now the equation for that of the phase constant and the attenuation constant for that of the good conducting medium, you will get the same equation. Okay, the unit will be different but the equation is same when the medium is good conducting medium. Now the equation for to find out the phase constant and attenuation constant, pi f mu into sigma, under root of pi f mu into sigma. This is the equation for find out the alpha beta. Phase velocity omega divided by beta, okay, is equal to under root of 2 omega mu into sigma. By using this equation you can find out the phase velocity. Now the phase velocity will be reduced in the good conducting medium, okay, because there is the sigma value at the denominator, and therefore the phase velocity is also reduced in good conducting medium. Now the intrinsic impedance for that of the good conducting medium is, the equation for that of the intrinsic impedance for the good conducting medium is j omega mu divided by sigma. Okay, now here again the imaginary quantity, therefore there is some phase angle. Okay, now and intrinsic impedance equation is this one, and the angle is 45 degree. If you find out the of this magnitude of this quantity, and the phase angle will be 45 degree. Okay, for that of the, I mean, there is the phase angle between electric and magnetic field of 45 degree. E leads by that of the H by the 45 degree in that of the good conducting medium. And the equation for that of the electric field intensity is E naught into e to the power of minus alpha z cos of omega t minus beta z ax. Okay, and H is equal to E naught divided by the magnitude of that intrinsic impedance is under root of omega mu divided by sigma. Therefore, we have replaced this eta by that of the intrinsic impedance equation, and then we have written the equation for H E naught divided by under root of omega mu into sigma e to the power of minus alpha z cos of omega t minus beta z minus 45, because the angle you will get the 45 for that of the when the wave is propagating through that of the good conducting medium, and therefore we have written here the phase angle 45. Therefore, the I and H waves travels in the good conducting medium. Okay, but it will attenuate. Okay, its amplitude is attenuated by that of the factor e to the power of minus alpha z, and the distance del through which the wave amplitude decreases by the factor e to the power of minus alpha 1, that is about 37% of its original value, is called as the skin depth. Okay, or it is also called as the penetration depth or skin depth. And this skin del value, we can find out that del is equal to 1 by alpha. Okay, now therefore it's we have equated e naught into e to the power of minus alpha into del, means if it will cover the distance del, its value will become 37% of the original value, and therefore we have equated e naught into e to the power of that equation is equated, and then from that one we have obtained the equation for that of the del, and del is equal to 1 by alpha. If you want to find out the skin depth for that of the good conducting medium, we have to use this equation, del is equal to 1 by alpha, and we know that how to find out the alpha for that of the good conducting medium. We have seen the equation for that of the alpha. Okay, and that equation we have to use, that is under root of pi f mu into sigma. This equation we have to use to find out the your attenuation constant for that of the good conducting medium. Okay, now these are the equations we have to remember, because the problem may be as numerical problem may be there. Okay, and you have to remember that equations, all these equations which we have seen. Now actually we will see that already uniform plane wave, we have seen the propagation of the wave through that of the different medium, and also we have seen the wave equations, and also we have seen what is the Poynting vector. Okay, now then we will see that the already some equations, already we have seen the equations for the wave equations, Helmholtz wave equation, partial then differential form equations. Okay, and then already we have seen these equations, that is the equations for wave. Okay, now here we have to see the concept of the phase velocity. Now if you see that the cosine function is called as the instantaneous phase of the field. Okay, and this phase we are denoting, which is the function of z and t, which is the omega t minus beta z. Okay, now this phase is moving with respect to that of the time. Okay, therefore the phase velocity is nothing but, that is we can find out for that of the lossless medium. Okay, that we have to find out, means it will cover some distance per unit time, means the velocity. Okay, and it will cover the distance dz with respect to that of dt in time dt, then you will get the velocity, and that is nothing but your phase velocity. Okay, now therefore we have omega t is equal omega t minus beta z is equal to pi naught, and then rearranging we are separating the z, and then we have determined dz by dt. Okay, after dz by dt is nothing but the phase velocity. Okay, that is nothing but some dz distance is covered in dt time. Okay, that is nothing but your the phase velocity, and therefore to understand this phase velocity concept, we have considered the equation, and therefore it will be omega divided by beta. You will get actually when you are taking the differentiation of this equation. Okay, because omega is constant, beta is also constant, and therefore dz by dt you will get that is omega divided by beta. Okay, and omega is equal to 2 pi f, you know that, and therefore the equation for that of the phase velocity will become 1 upon under root of mu into epsilon. Now beta is equal to 2 pi by lambda, and therefore that lambda will get cancelled, and 2 pi. Okay, and therefore you will get the equation for that of the phase velocity is equal to 1 upon under root of mu into epsilon. Okay, now how this equation for that of the beta is also obtained, that is 2 pi by lambda, that concept is shown here. Now the distance along the direction over which the instantaneous phase angle changes by the 2 pi radian. Whenever the angle is changes by that of the 2 pi radian, means it will cover the distance lambda. Okay, fixed distance lambda. It will cover the distance when the wave is covering the distance of lambda meter, then its angle of phase angle is changed by that of the 2 pi radian. Okay, now therefore we can write that there is beta into lambda is equal to 2 pi, and therefore lambda is equal to 2 pi divided by beta, or beta is equal to 2 pi divided by lambda. Okay, now these are the phase velocity concept. Okay, phase velocity already we have seen that omega divided by beta is lambda into f. Okay, now these are the concepts, or the propagation of the waves through that of the different mediums. Okay, that we have seen that, and also now the concept of the polarization and reflection and refraction concept of the wave, we can also see here. Polarization means what? The polarization of the wave means what? That is the orientation of the electric field with respect to that of the ground is called as the polarization of the EM wave. Okay, now the polarization, that is the orientation of the field or the curve traced in the by the electric field in the medium is also called as the polarization. That is the polarization is the curve traced by that of the end point of electric field, instantaneous electric field. Okay, sometimes the curve may be the straight line. At that time we are saying that this is the linearly polarized electric field, or the EM electro wave, that is linearly polarized. And when the curve traced by that of the electric field is circular, okay, in the free space with respect to that of the time, then we are saying that that polarization is circular polarization, means that vector is moving or tracing, or tip of that vector is tracing the circle in the field in the free space. Then we are saying that this is the circular polarization. And when the tip of the electric field will trace the curve like elliptics, then we are saying that elliptical polarization. Okay, now this is the polarization. There are three types of the linear polarization, circular polarization, and elliptical polarization. Okay, now there are some conditions actually uh, should be satisfied to get the specific type of the polarization. And to understand this, the concept of the polarization, we have to consider one of the wave. Okay, now we have considered this is the one of the electric field equation having the two components. That is, the first component is along that of the x-axis, another component is along that of the y-axis. That electric field is having the two components along the x and y-axis we have considered here, and the real part of the component which is along that of the x-axis is ex not cos of omega t plus kz plus phi x. K is nothing but here the propagation or wave number. Okay, now Ey is the component along that of the y-axis. Okay, now we have considered here whenever the linear polarization is there, what happens actually, there is the phase angle between that of the two components, that is the component along that of the x and y-axis is the phase difference between these two component is n pi, where n is equal to 0, 1, 2 and 3. Uh, then when the phase difference is n pi or multiples of integers, then we can say that the polarization is linear polarization. And or sometimes actually one of the component may be zero, that is only one component may be present. At that time also we can say that the wave is linearly polarized. Okay, now the circular, this is the condition for linear polarization. Then circular polarization, the condition is that the magnitude of both the components which are present along that of the x-axis and y-axis should be the same. This is another condition. And the phase difference between these two components must be, for that of the clockwise, it is 1 by 2 plus n pi, n is equal to 0, 1, 2 for that of the clockwise, and for that of the anti-clockwise 1 by 2 plus n bracket close into pi. Okay, now here n is equal to 0, you can substitute here n is equal to 0, then what you will get, pi by 2. When n is equal to 1, then you will get, that is 3 by 2. Okay, then 7 by 2 like this. For this only you will get, that is the clockwise uh, polarization. Okay, that is the direction will be changed. Okay, that circular polarization, this is the condition. And for that of the elliptically polarized, that is magnitude of the component along that of the x and y is not same. This is the first condition. The second condition is that the phase difference between that of these two component must be multiples of 1 by 2, 3 by 2, 5 by 2, 7 by 2 like this for clockwise. Okay, and minus 1 by 2, minus 3 by 2, 4, 5 by 2 and 7 by 2 for anti-clockwise. Now, and or that phase difference should be plus or minus pi by 2 into n. Okay, for greater than that of the 0, and whenever the phase difference is greater than 0, less than 0, when n is equal to 0, 1, 2, 3. Okay, now just elliptical shape is formed, and these conditions will be satisfied to get the elliptical polarization. Now this is the shape of ellipse, or the curve is traced in by the wave. Okay, axial ratio is the ratio of major axis to the minor axis. Major axis of the ellipse is here. This is your major axis. This is the minor axis, and this major that ratio should be between that of the 1 to infinity. Okay, now this is the linear polarization, circular polarization, or the polarization of the wave. Okay, then There is the another part we have to discuss is the reflection and refraction of the waves, okay, and also transmission lines and with waveguides. That part we will discuss in the next lectures. Okay, with that next lecture schedule is you remember the next lecture schedule also 23 and 24th November, and on that day I will conduct the lecture, and in that lecture I will discuss about the reflection of the wave, refraction of the wave, and the transmission lines also. Okay, today here I will stop, and if you are having any difficulty regarding these wave equations, pointing theorem, pointing vector, and the reflection of the